Hi, I'm Sean Ahmed, CEO of Causal Express, talking about LLMs, VLMs, and Agentic AI, what they are and how we can help your business with them. LLM stands for Large Language Models. Some LLM use case examples are customer service chatbot, coding assistant, sales agent bot, document summary, chronology extraction, checking the business controls to ensure they match relevant standards, and highlighting differences between two documents and text, finding missing parts and discrepancies. VLM stands for Vision Language Models. Some VLM use case examples are customers can search products based on a picture of a product they came across, radiology and other health applications, or matching faces and face descriptions in criminology. What is agentic AI? AI agent that specializes in a certain task and does that task calling functions and APIs based on a natural language input. Agentic AI examples are an agent that prices an option in markets, filters and books a vacation rental and makes a payment. We can create also teams of agents who would work together to complete a task. For example, for designing an app, we can have an agent that writes code, an agent that reviews code, one that tests code, and one that approves code, all together working to accomplish a task. So foundation models are existing trained models that are available in the market. They are pre-trained closed source models such as GPT, Cloud, and pre-trained open source models such as Llama, Gemma, Mistral AI, DeepSeek. Main difference is that the ability to customize them. Open source models can be customized while closed source ones cannot. Generic foundation models are not optimized for tasks, and many businesses need customized models for maximum productivity. That's why a company like us can take an open source model and customize it based on the needs of the business. So ways to enhance model performance and customize them. One of them is RAG, which is basically using your proprietary data. One is fine-tuning, and one is RLHF, which is reinforcement learning with human feedback. RAG doesn't change the foundation model, but enhances it with your proprietary data. Fitting the data together with the prompt fine-tuning and RLHF lead to change in model themselves, creating a customized version for the clients. RAG, in basically more details, with RAG your proprietary data is made useful using tokenization of data, embedding them into a database stored on a vector database equipped with vector similarity metrics and vector search. And vector databases are Pinecone, VV8, Quadrant, ChromaDB, Amazon OpenSearch, Azure Cosmos DB, and so forth. And vector search is usually done based on vector similarity. When it comes to fine-tuning, which is a method to customize LLMs, the most common type of it is supervised fine-tuning. You need a data set of labeled examples, typically in the form of input-output pairs, prompt-response pairs for an LLM. And this can be done using full fine-tuning, which is expensive, which is basically updating all the parameters of your model, of that open source model, in the way we train a network. Standard training loop, forward pass, calculate loss, backpropagation, gradient update on all layers of the model. And it can also lead to catastrophic forgetting. And then other option, which is increasingly more popular, is PEFT, parameter efficient fine-tuning. Only update a small fraction of the parameters in the model, often less than 1%, making the process much more efficient. The core idea is to freeze the majority of the pre-trained weights and inject a small number of new trainable parameters. And the most popular type of it is LoRa, which is low rank adaptation. Freeze weights and train a side matrix of parameters, but increases latency. And it's basically a specific fine-tuning that improves instruction following an alignment, often implemented using either full fine-tuning or PEFT method, and that is instruction fine-tuning. So you collect a data set of instruction response. There can be simple tasks such as summarize this text to complex multi-turn conversations, and you use this data set to fine-tune your LLM. So this was a very brief introduction to fine-tuning. Then it comes alignment, or RLHF, reinforcement learning human feedback model, is a post fine-tuning alignment step that a lot of times is needed to make the basically the model, the customized model, behave more human-like. It uses human preferences to further refine model behavior. It's a crucial step after supervised fine-tuning and human feedback to train a reward model is used, which that guides a reinforcement learning algorithm, such as PPO, proximal policy optimization, to further fine-tune your large language model. Allows one to learn subtle nuances of good or bad responses that are difficult to capture with just simple instruction fine-tuning. So you have a reward model training, which is generating multiple responses from the supervised fine-tuning tuned large language model for a given prompt. Human annotators rank or score these responses based on quality, helpfulness, and so forth. This human feedback data is used to train a separate reward model, which is often a smaller large language model, to predict human preferences. The reward model learns to assign a high score to preferred responses and a low score to not so preferred ones. And this is done with a PPO, proximal policy optimization, or which is used for reinforcement learning training of this model. So, inference improvement for LLMs. How we can improve the performance of your LLM when it comes to inference. We know that optimizing is all about reducing the computational load of it and memory usage to achieve lower latency, basically faster response, and higher throughput, more requests per second. Can be done using quantization with a compression technique that reduces numerical precision of the model's weights and activations. We can do KV caching, key value caching. Key value is used basically as tensors within transformers. For previously processed tokens, these can be stored in a dedicated memory area, and that's called KV cache, and this can speed up the process. Model distillation is useful here. Knowledge distillation involves training a smaller student model to mimic the behavior of larger, more powerful teacher model. Student model learns from the teacher's outputs and tries to replicate them. So this way the model becomes much smarter, much smaller, and equally effective, more or less. Or we can also do efficient batching and serving frameworks that also help with improvement in inference time, basically speeding up and using less resources. So there are other LLM architectures for long memory or faster inference we can implement for you. You can see here side by side, you see transformers, you see RWKV, and you see here Mamba. Transformers are not the only available architecture for making LLMs. The other ones, Mamba, which is instead of relying on a self-attention mechanism, is based on a class of models called state space models, which have a long history in control theory signal processing and allows the model to selectively remember or forget information in the sequence based on its content. In simpler terms, it's like a smart memory mechanism. Processes sequence token by token, deciding which information to keep in its hidden state and which one to discard. And it's much faster, especially for long sequences. RWKV, which stands for acceptance weighted key value, is also a neural network architecture for sequence modeling that has the best of both worlds, parallelizable training of transformers, and also efficient constant memory inference of recurrent neural networks. It's much faster in inference than transformers, and it can be also trained using teacher-student model, basically, knowledge distillation. So embedding and customized embedding, basically fine-tuning embedding models to recommend items such as products, articles, movies, music based on semantic similarity to a user's preferences or other items. Fine-tuning can learn what similar means in the context of that user behavior or domain-specific attributes. For example, when you are embedding the movies in the streaming services, one specific user can have a particular viewing history that it can help fine-tune the particular embedding of the movies for this user. For example, he's very interested in sci-fi thrillers and dystopian dramas. So we can create an embedding of the movies that creates a closer embedding these stances between sci-fi thrillers and dystopian dramas because this user happens to like both of them very much. So this way, the user who enjoys both can lead to more personalized recommendations for that user. Or news aggregators, or even for tax purposes, certain business product pairs and combinations have to have similar embeddings for tax purposes based on their tax regulations.
Hello, what's happening?
So, conclusion, LLMs, VLMs, and agentic AI are capable of automating a large variety of tasks within a large variety of businesses by digesting information and producing meaningful output. But tuning them to your business, selecting the right models optimized to your hardware and infrastructure, etc., needs expertise, and we have that expertise. Thank you for tuning in. Contact us and visit us at causalexpress.com. Thank you.